So now we want to look at a short example involving the Rlc circuit. And just a reminder, if I have a capacitor and I have an inductor, and these two elements are connected by some wire. Okay. In this case, remember that we saw if the capacitor was initially charged to some initial charge Q naught, then the current would flow through the capacitor and it would charge up the plates as it moved, but the back EMF through the inductor would then want to cause the current to reverse direction, and you just get this sinusoidal charging of the plates, sinusoidal flow of charge. And so the charge on the plates follows this form Q naught cos times omega t, and we saw that omega was equal to 1 over the square root of the inductance times the capacitance. So, some things to note. Okay, some things to note. Remember that the frequency would then be 1 over 2 pi of the square root of Lc, and the period is equal to 2 pi times the square root of Lc, right? And what you can take from this is the smaller the values of L and C, or at least the smaller their product is. Okay, if I have a small product for L and C, then I'm going to get larger values for omega. Whereas if I have large values of L and C, then I'm going to get smaller values of omega. And if you think about it, this should make sense. C is the capacitance, or the ability to store the charge, and L is the inductance. And the inductance is the rate at which the current changes. Okay, or you can I shouldn't put it that way. The inductance is the ratio of the flux through the inductor to the current through the inductor. And the larger that product is, okay, the larger that product is, the more slowly the current is going to change. Okay, the larger that L and C are, the more slowly the current is going to change. So this process will take a longer time, which is what we have predicted in the equations. The larger the product, T will be larger, and so the longer this process will take. And so what that means is that the charges flowing through the circuit are going to flow, the individual drift speed of a charge is going to be a little bit slower for large values of L and C. And for smaller values of L and C, it'll be faster. And that just means that the omega, the frequency, is the frequency with which the current is going to reverse direction from flowing one direction back to the next. So for really large, or I'm sorry, for really small values of LNC, the charges are just going to move back and forth really quickly. Okay. Whereas for smaller values of LNC, or I'm sorry, small values of LNC, they'll move back and forth very quickly. For large values of LNC, they'll move one direction and then they'll reverse and move the other, and then they'll reverse and move the other. It'll be a much lazier process. The current, remember the current is the derivative of charge. So the current in this case would be given as negative Q naught times omega sine of omega t. And Q naught omega would equal the initial amount of current in the circuit. Or not the initial, but the maximum amount. Apologies. It's the maximum amount of current. Let me write it like this. And so the maximum amount of current would be Q naught times omega. And if we want to do an example here with actual values, so let's let our capacitance have a value of, let's say, 1 microfarad, which is 1 times 10 to the negative 6 farads. And our inductance is going to have, let's give it 10 millihenries. I'm sorry, let's go ahead and give it 10 henries. Let's make this a rather large inductor. So L and C, in that case, omega is going to be 1 over the square root of LC. And so omega would be equal to 1 over the square root of 10 henries and 1 times 10 to the negative 6 farads. So this is 1 over the square root of 1 times 10 to the negative 5th seconds squared. Okay, so remember henries times farads gives you seconds squared. Okay, and you can see that from this formula right here. Henries times farads has to give me seconds squared, so that way when I take the square root, that gives me seconds. And so if I take this value, 1 divided by 1 times 10 to the negative 5 square rooted. So 316. 316.2, but for good enough for government work, we'll call it 316. So this is 316. You know what? Let's not call it hertz. This is going to be rads per second. Okay, so 316 radians per second. And a regular frequency then of 1 over 2 pi would give us 316 divided by 2 pi. 50.3. 50.3 hertz. So these charges are going to flip back and forth, okay, essentially 50 times a second. And let me be very formal about this. What this means is the plates are going to go from charged in one configuration to being charged in the opposite configuration and back again 50 times a second. Okay. So this is a very rapid process in this kind of situation. This is a very rapid process. Okay. And the period is going to be very small. The period is going to be the reciprocal of this. 1 over 50 is like 0.02. So this is going to be roughly 0.02 seconds. I'm ignoring the 0.3 here. Good enough for government work. So about 2/100ths of a second is what it takes for that process to happen. Okay. And again, once the plates are charged with a configuration, they want to naturally move off because the plates naturally want to be discharged. But it's the back EMF in the inductor that then causes the current to reverse its direction and recharge the plates. Okay? So, essentially, I think that that's good enough. So let's do one more thing and say, okay, what is the initial current? Well, the initial current, we need to know what the initial charge is. If I charge these plates up to, let's say, 1 picocoulomb, so let's say Q is 1 times 10 to the negative 12 coulombs of charge. And my current would then be Q naught times omega, and Q naught 1 times 10 to the negative 12 coulombs times 316 rads per second. And so this is going to be 316 coulombs per second. 316 times 10 to the negative 12 coulombs per second, or 3.16 times 10 to the negative 10. Coulombs per second. So a minute amount of charge. Okay, a fairly minute amount of charge is what we have here. Or I should say a very minute amount of current, because this is technically amps, right? This is technically amps. And let me write this a little bit better. Okay. So there's an explicit example of oscillations in the LC circuit and some of the types of information you can draw from it. And now let's turn our attention to the RLC circuit. Okay. So an RLC circuit, if I have a capacitor and I have an inductor, and I have a resistor, and I have all of these connected together. Okay, so I have a switch, and once again, let's assume that my plates are initially charged to a value Q naught. Okay, now what's going to happen when I close the switch? Well, without the presence of the resistor, okay, without the presence of the resistor, then we would have just the LC circuit we just looked at, right? But what happens when I put a resistor in here and then I close the switch? The current will still start to flow. The plates will still try to discharge, but I don't have conserved energy anymore. Okay, well, I technically do. I can account for the loss of energy, but the resistor is going to dissipate some of the energy each cycle. Okay, so as the current flows through the resistor, that the resistor is going to heat up and dissipate some of the energy as heat to the environment. So each cycle, there's less internal energy in the system available. And so as a result, the resistor acts as a dampening force. Okay, so the resistor acts to dampen the oscillatory current. So I close my switch, my current will flow, and then it'll flow back. And each time the current will be smaller with each oscillation. Okay, so how do we describe this? Well, remember that the power through the resistor is I squared R, right? The power through the resistor is I squared R. But we're going to go ahead and call this a loss of power because it's dissipative. The energy in a capacitor, if you'll recall, is going to be 1/2 Q squared over C. We've seen that before. And the energy in the inductor is going to be 1/2 Li squared. Okay, so the energy being supplied by the capacitor and inductor is going to be equal to 1/2 Q squared over C plus 1/2 Li squared. But remember that power is the time derivative of energy. Okay? So what we're saying is this is the available energy in the circuit at a given instant, and this is the energy being dissipated. Okay, so using conservation of energy, we can say this. I'm going to take the time derivative of the potential energy. So the time derivative of this is going to be Q over C dQ dt. And this is going to be, and by the way, so use the chain rule, right? So the derivative of Q squared is 2Q over C. The 2 and the 1/2 cancel, so that's where the 1/2 goes. And the same thing is going to happen with the Li squared here. L is a constant, and so my current is going to be my function of time, so that gets differentiated. The 2 comes down, cancels with the 1/2, and I would have Li di dt. Okay? But remember that dq dt is the current, so this is I. So the power delivered by the circuit elements has to equal the power dissipated by the resistor. Okay? And as a result, so I have this equation, right? If I write this out completely and I add I squared r to the other side, I'm going to get, in order of decreasing powers of Q, I'm going to have Li d squared Q dt squared plus actually, you know what, let me write it like this first. I changed my mind. Let me write it like this first. It'll make a little bit more sense, and then we'll make the transformation. So Li di dt plus Q over C times I plus I squared R is equal to 0. And I can get rid of an I everywhere. And that leaves me with this equation, L di dt plus IR plus Q over C equals 0. And now I can write my I's in terms of the derivatives of the charge. So this is going to be L d squared Q dt squared plus R dq dt plus Q over, let me write this as lowercase q. Q over C equals 0. And this is a second order linear differential equation. And this is a simple harmonic equation except for the middle term. So the middle term is a damping term. Okay. Now, there are multiple cases. Okay. So what will happen will depend on the value of R. And if you think about it qualitatively, this should make sense. If I have a really small value of R, okay, if I have a really small value of R, then what will happen is the power dissipated by the resistor into the environment will not be very much per cycle. So for small r, okay, for small r, if my current is supposed to be oscillatory, so what I'm about to draw would be the current without the R term. If my current would be oscillatory, actually, you know what? If this is a cosine, then it needs to start up here. Okay, so that is my current without any damping. And for small r, what will happen is each cycle, only a little bit will get dropped. It needs to stay in phase. So my current would get damped and it would decrease on both sides of the axis. Okay, I don't know how clear that drawing is, but the current for small r is going to do this. Okay, that's the overall idea. And it'll be bounded by these curves. For the critically damped case, okay, if your R is just right, then at the critically damped case, then your current will essentially not cycle back. Okay, you'll almost get through one cycle, but you won't get through a complete cycle. And if your resistor is larger than that value, if it's larger than the critically damped case, then essentially your oscillation will die out well before one cycle, right? And so if you have an extremely large resistor and it dissipates all of the energy, essentially, before the capacitor and inductor can work to cycle the charges back, then your current will effectively die off very, very, very quickly. So those are the three cases, but the most interesting one of those is the underdamped case, or the small r case. And I'm not going to go through the math for the solution to the differential equation, but in the case of small r, underdamped, we have the solution QT is equal to the initial charge on the plates times e to the negative RT over 2L, and the 2 is a new thing, but the e to the negative RT over L is the same thing as e to the negative t over the inductive time constant. So in the critically damped case, this is effectively equal to negative t over 2 tau. Okay, so the 2 just comes out of the way the math works for damped systems. And then cosine of omega prime t plus, if we have a phase constant, if we don't start our stopwatch right at the maximum charging of the plates, for example. Now, the omega here is not going to be quite as simple as in the original case, okay? The omega here, the angular frequency that this oscillates at, is going to be equal to 1 over LC minus R over 2L square rooted. Or I'm sorry, squared, and then the whole thing square rooted. So the presence of the resistor does indeed act to change the frequency of the LC circuit by itself. Now again, if R is really small, then this term is going to be really, really small. If R is small, then this term is going to be really small, especially since this is squared, and this is only a very small correction to your omega, right? And this is effectively going to act to make your omega smaller, and that means your period longer. So this is going to act to increase the times that these interactions occur, okay, over which these interactions occur, I should say, right? So that is the RLC circuit for the underdamped case, okay? And again, this is the most interesting of the solutions. And if you look at the diagram that I drew here, it might be even easier to redraw it here. Here are my axes. And I'm going to have something like this. Ignore that little blip there. And so the bound of this line, okay, it's really hard to draw on the pad, but the bound of that line and the bound of this line, those lines represent the exponential decay part. Okay. The way that the oscillations decay is dependent on this exponential term, and then the actual oscillatory nature is due to the cosine term. Okay, so we have that. So that is the oscillatory system for the RLC circuit in the underdamped case. In the next set, we will start looking at the AC circuits and how each piece is involved in the operations of an AC circuit. And then we will look at E and M waves. And so stay tuned.